Okay, so thanks for having me, and I'm sorry I couldn't make it. I was actually excited about coming. So the topic I'm going to talk about is, as it says here, deep learning and heterogeneity. And I don't know how we do questions here, but I guess you can raise your hand or unmute and jump in if you have questions, but I'm going to structure it so that I'll talk for a little while, and then from time to time I'll pause to see if you guys have questions. Usually we would do this in an interactive session, but we'll do the best we can. Okay, so just for the heck of it, I thought it would be interesting to start by showing you where kind of the state of deep learning today is. I asked OpenAI, or GPT-4 in particular, to create a clever quote around deep learning and public policy, and this is what it came up with, which I thought was pretty funny. I'm assuming all of you are laughing right now because you're all muted. So. Okay, let's see. So I don't think I have to convince you guys of the importance of thinking about heterogeneity. Essentially the idea that different consumers, different economic entities, different firms, whatever your unit of analysis is at the economic level, exhibits some kind of heterogeneity in terms of their behaviors. Usually we think of these differences or this heterogeneity as being economically meaningful, and in the sense that we want to vary our decisions or design policy or evaluate policy or target or personalize kind of our policies according to that heterogeneity. But even if you're not interested in personalization, so my entire talk is going to be about personalization and why I think it's a good thing and why deep learning in particular is suited to this problem. But even if you were not interested in that, just for the sake of accuracy or inference or getting kind of the right answer at the aggregate level, accounting for this heterogeneity is still important, and there's a whole literature on kind of thinking about where biases come up if you ignore heterogeneity, right? As Simon pointed out, my talk or presentation here is going to be on the practice of estimating and using heterogeneity. But in order to get there, I'm going to tie it to the theory that you've just seen. I'm assuming Whitney went through kind of the double machine learning ideas, and I'm going to use similar ideas here, just kind of an extension of what he and his co-authors have worked on before, but in the context of deep learning.
Something went wrong. Please try again.
Say that again?
All good, all good.
Okay. There's a funny person in the audience.
Cell phone. Siri went off.
Oh, Siri went off. I see. Okay. So let's talk about personalization. So how do we think about personalization, right? So this is your, the math equation on personalization. So the idea is we have information about individual entities. I'll think of consumers. You can think of whatever, you can think of patients. You can think of any other kind of subject of the treatment that you are designing. And out comes a decision or a policy, D sub I. And just to be clear, I'll use D here, but then when I get to the kind of treatment effects, I'll switch to T for treatment. So I'll warn you as I go along. But this is what we want to do. But this is not complete. So we think of designing policies or treatments to maximize or to kind of address some particular objective we have in mind. So let me spell this out a little bit in more detail. So let's go piece by piece, and this is typically what we all do, right? So if you're writing down a model, estimating a model, and then using some kind of, or doing any kind of counterfactual, this is what you're doing. So can you guys see my cursor?
Yeah.
Okay. So in particular, let me start with kind of the objective here. So I've used pi here for profits, but you can easily exchange this with constructs like welfare or anything else that you care about. So this is the economic kind of objective that you have in mind. and it takes as argument a bunch of things. In particular, there's the decision, right? Now, what do I want to do to kind of deal or to address this objective? Well, let's say it's prices, so I might want to maximize profits by choosing an appropriate price. Now, this decision, of course, has to be picked out of some decision space. So you may have, you may say, well, I don't have any constraints on prices, or you might say, well, I have a discrete set of prices because I think prices should end in 99 or whatever, right? So the decision space is kind of within your control. From those, you're going to evaluate different decisions and then look at the objective to say, okay, how is it doing? Now, there's other things in the objective. Clearly, there's going to be uncertainty, right? So, and how we deal with that is something we'll have to think about. There's going to be some data that you're going to bring to the table that'll allow you to do stuff. But the most important piece that we're going to talk about today is going to be this type, this theta sub I, right? And this is, say, a vector of, apologies. It's a vector of parameters that we have to kind of define in some meaningful way. And once we have this objective, well, what do we do with uncertainty? We typically just integrate it out. And then we take this entire expected kind of objective, if you will, apply some decision criteria like maximize or minimize or satisfy, whatever else that you want to do. And that gives you an individual level personalized policy. Does that make sense? I can't see your heads nodding up and down, so just say yes if that makes sense or if you have any questions.
It makes sense. Also, would it be possible for you to post slides on the GitHub like afterward?
Yes. So I'll send these slides. Sorry, I was kind of a just-in-time delivery system here, but I'll send these to Simon and he'll post those.
All right, thank you.
Yep. Okay, so the goal is to ultimately come up with this personalized policy.
Sorry, there was another question. Can you?
Yes.
Oh yeah.
Yes, like about this framework, do we think of it as like a static framework, or do we also think of it like as incorporated, like dynamic frameworks which might have some state variables by which you like individual?
Right. So that's a great question. So the way I've written it up right now, I have said nothing about what the objective or the time frame of the objective is supposed to be, right? So let's go into that a little bit more. And then I'll talk about it. I don't have slides on this, but I have a paper that I'm working on that shows how you can do this with dynamics as well. But let's hold off on that. And if I don't address it, ask your question again. Any other questions about this framework? No? Okay. So like I said, the focus is going to be on this type, right? And there's many ways in which we deal with this, and I'll talk about a few, and then I'll propose one which should be pretty straightforward, kind of conceptually, but again, we can talk about that some more. Okay, so let's start by the kind of related to the question that was asked. So typically, if you're an applied economist or a marketing person like me, you think of a particular structural model, and usually that structural model can be defined by a finite set of parameters, right? So if you have a demand model, let's say you've got, and it's a really simple one, you might have an intercept and a slope, and those would be the parameters. If you have a choice model, there's going to be a vector of parameters. I've just indexed those parameters with I. And the other two things, here's the kind of switch I told you about. There's a set of outcomes that I'm calling Y, and there's a set of treatments that I'm calling T. Now, treatments could be prices, they could be advertising, they could be kind of inputs into a production system, whatever whatever your application happens to be. Your entire economic structural model is represented by this L here. And the only requirements that we have on L is that it's a per observation loss function. So it could be a negative log likelihood, it could be a GMM objective function, but it just has to be smooth in the parameters. And so you should be able to take derivatives of this loss function. Okay, so that's the only requirements that we have. Now, of course, how do we deal with this heterogeneity? And there's various versions. I'll tell you the most popular approach. So the most popular approach is to do nothing. right? That's 90% of papers in economics will say, yeah, there is heterogeneity, but I'm just going to model kind of the average patterns, if you will. And so let's just ignore that part. Of course, that's not what we want to do. So I'm going to pull a slightly different trick. I'm going to use this idea that you've seen now, hopefully across a bunch of other lectures, heterogeneous treatment effects. So I'm going to project theta I onto a set of characteristics, which could be high dimensional, right? And it's an old idea. This is not a new idea. But typically, when this was done in the past, theta of x was thought to be a linear function. So it would be theta prime x, if you will. And that would become an interactions effect. So let me pause here because this is kind of an important piece. Is this clear as to what I've just said?
Yeah.
If you're raising your hand, I can't see it. So just speak up. Any questions? No? Yeah, maybe this will become clear as I go on. Okay, so essentially think of it as follows. Let's take a simple example. If our example was y is equal to a plus bx plus error, that's our model. Then L would be the mean squared error, let's say. That's what we are choosing. So that would be, y minus beta prime x whole squared, summed up. And what we are now doing is we're changing that. So we're saying instead of having alpha and beta, what we now have is y is equal to alpha of x plus beta of x times treatment. Okay. And the rest of the assumptions remain fixed because those were economic assumptions. Okay. Assuming no questions, the second thing I'm going to do is I'm going to say, okay, since I don't know what this function theta of x is, it's some non-parametric object, I'm going to approximate that using deep nets. And this is where the difference between how deep nets are, like how we are using deep nets as opposed to kind of the typical use of deep nets. Typically, we project y onto deep nets. Here, we are projecting the parameters onto deep nets, onto the deep net space, if you will. Okay, so the first thing we did was we said, we don't have theta I, we're going to replace theta I with theta of x, where x can be whatever information you have about the consumer, about the entity. Second, I'm going to make the assumption that that theta of x can be approximated by a deep neural network. And of course, third piece is I have to be able to estimate this deep neural network. So the entire framework can be written like this, or depicted as like this. So when we usually do basic models that in IO or in labor or wherever else, it's the red part that kind of we talk about, right? So there's some output Y, there's some kind of treatments of interest, whether they are prices or capital or labor. And then all the economics is subsumed within L. So you get a parametric kind of model, a structural model that's L of y, t, and theta, and we usually estimate theta. Now we're making theta a function of x. That's the first part. And in particular, that function is going to be a deep net. You guys with me?
Yeah.
Yeah, okay. And so it's not, so you've changed very little. Like the advantage of this framework is that all your thinking happens in economics space. And the place where you do not have theory, it's there, it's only there where it's that a-theoretic kind of piece that you stick in a deep net. So the interpretation of theta remains as if it was in the economic model. Okay? So the model is still parametric and it's defined by economic structure, not by statistical structure. Okay. So then what do we do? Well, in principle, all you have to do now is take your loss function or your likelihood or your GMM objective function, whatever you've kind of designed L to be, and you stick it into code. And standard tools like, TensorFlow or Torch will do this trivially. Right? And if we have time at the end, I'll show you a quick demo how easy this is to do. Okay. Now, suppose you did this, you would obviously want some kind of theoretical guarantees that this makes some sense, and I'll talk a little bit about that. Okay. And but for most part, I'm going to show you kind of practical applications of this framework, what it's capable of doing and how far you can push it. Okay, so let me break this down. And I'm going to go over theory more intuitively. I mean, obviously, you can go read the papers. I can share those also with you. But so the goal is to approximate theta of I with some estimator theta DNN of X, okay, of X sub I here, right? So for a given individual, if you will. So the first piece is to say, well, can I actually take the true heterogeneity and approximate that as a function of covariance? Right? That's an assumption. I can't prove that to you, but that's an assumption we are making. And I can make some arguments why I think that approximation is reasonable in the context I'm studying, but that's going to be an empirical question that you'll have to grapple with. Obviously, this will depend on kind of the richness of X's, the relevance of X's, and so on. Okay. So can we actually take true heterogeneity and then approximate it with observables? That's this first piece. The second piece is, even if I knew that this function existed, can I now approximate that unknown function by deep nets? Right? That's the second piece. And the third piece is, let's assume that that approximation makes sense, that we can actually get a deep net. Can I now estimate that deep net with my data and get a reasonably good kind of estimator of those? So that's kind of the usual three pieces of trying to get at something. And in the paper, what we do, well, let's go one by one. So the first piece is like, okay, do we have a rich set of X's? In most practical applications that where you would think of applying this, the answer is going to be yes. So what I've done over here is just kind of been a little silly, but I've put in all the covariates that Facebook gives you access to if you're running a targeting campaign on Facebook. And there's thousands upon thousands of characteristics that you can target on, right? Now, is it enough? That's kind of, it's a subjective question. But think about the following. Suppose I have 10,000 variables about each customer, and I still believe that there is unobserved heterogeneity. That unobserved heterogeneity in some sense would have to be kind of independent or orthogonal to the heterogeneity that's observed, right? So something else that needs to be there. So I'm going to make the assumption that you do have a rich set of characteristics. Okay? And typically, if you have cross-sectional data, other approaches like fixed effects or even random coefficients are not going to be terribly useful. Actually, a quick aside on that, right? Even if you could do fixed effects or random coefficients, the problem is for policy and for targeting, you need to be able to predict, let's say, a new customer's type, and you can't do that with fixed effects. So you would have to project it onto a set of X's anyway. So you'll be back here. Okay, second piece and third piece. Well, that's going to be that's part of the theory. Like I said, I'm not going to go into the theory part here. You've already seen some version of how you prove these things, hopefully in other lectures. But the intuition is as follows. Excuse me. One is, can we approximate an unknown function with deep nets? And there's a ton of theory on that. But essentially, you're relying on what are called universal approximation theorems. So as the complexity or the flexibility of your deep net grows, you're going to be able to approximate any smooth function. Like, is that enough? Well, that depends on your context, but it's a large enough class that I feel comfortable that this is a good class to kind of work. Deep nets are a good class to work with. The second is, can we estimate it? Well, here we rely on sample sizes kind of increasing. So as you have increasing, as your n goes to infinity, you're going to kind of get to the truth. And this requires some formal proof. And we have a couple of papers, one in Econometrica, and then another working paper that kind of says, yeah, you'll be able to do something like this. Okay. And the proof basically gives you rates of convergence, and that's written down in the paper. And these are not optimal rates, but these are fast enough rates that they allow us to do semi-parametric inference. So if you've seen the double machine learning stuff that and kind of understood it, essentially this kind of gives us a way of using NUE94 to do inference moving forward. Okay, again, so that's all I have for kind of the pure theory piece. Let me talk more about the practical aspects of this. So why use deep nets and why not use something else, right? So there's tons of other ML tools. There's like, you know, sparsity based kind of ML tools like the lasso or forests or boosting. Like there's a whole bunch we can talk about, like why deep nets. So first, like some of the others, deep nets are universal approximators. So they can approximate any smooth function. But they're also practically incredibly easy to use, and they're scalable. And you can kind of scale these up or down. So what I mean by that is you can make deep nets as complicated as you want, or you can make them as simple as you want, and you can still kind of use them. They're like polynomials that way. You can have like, you know, your order of the polynomials is kind of within your control. So that controls kind of the flexibility of this approximating class that you're using. And there's this misconception that for deep nets, you need tons and tons of data. It's definitely true that if you want to approximate kind of some high dimensional complicated function, you need more data than less data. But think again of like polynomials or sieve estimators, where, you know, the complexity of your approximator is within your control. So if you have less data, you're not going to put in like 17, you know, 17th order polynomials. You're just going to use maybe x and x squared. Similarly here, if you have if you don't have really large amounts of data, you can build simple deep nets. Keep in mind that even the linear regression is a deep net, right? It just doesn't have any layers. It doesn't have any complexity in it, but it still, you know, it still falls within this class. But the most important reason to use deep nets is what I call structural compatibility. It's truly plug and play, and it's easy to see this with an example. So imagine that your model is this really simple model, right? So you have a utility function. It's got two, and this is the parametric version of the utility function. So you've got like, you know, some parameters alpha and beta. You have some treatment t sub I, and you've got the usual logit type error stuck in there. So there's epsilon I. And if you make the usual assumptions, you end up with a probability that looks like the logit probability, okay? The only thing we are doing is we're saying, oh, look, we have alpha sub I now and beta sub I. So instead of having just alpha and beta, we added heterogeneity. And then we're going to change that to make alpha and beta functions of x's. But what I want you to see is by introducing deep learning, we did not change the economics of the problem. The structure remains exactly the same, and the interpretation of the objects remain exactly as they would under here. So this beta of x still is the marginal effect of t on utility. It's just a function now. Okay, so if you think of that, then you can say, well, I can now do marginal effects. I can do willingness to pay, elasticity, surplus, whatever I want to do. If t were prices, I can interpret beta as the price effect or the marginal utility of income, whatever you know, however you think about the effect of prices in utility, right? And so it gives you the economics back rather than kind of taking it away from you. So it's not a nuisance function anymore. It's something that you actually care about, and you might want to kind of use in counterfactuals or, you know, get kind of inference or and do something with it. Yeah, let me pause again here to see if there's any. I've kind of thrown a bunch at you, so let me see if there's any questions.
I have a question. When x's are correlated with the treatment, could you get a bias in the sense that the mean beta on the treatment is no longer the way we would normally interpret it as the mean causal effect?
Yep. So everything that you probably saw in Whitney's lecture or any other causal inference lecture applies here. So I'm going to pretend, and in my applications, you'll see it'll always be true, that T is a randomized kind of treatment. Now, so in the paper, we talk about what happens if, if the treatments are endogenous, and then you get into kind of other things. So let me give you an example. This framework that I've just shown you, let me go back here. Nothing stops you from doing like diff and diff. So if you think that I need to do diff and diff to get at causality, well, so be it. That's just a loss function. Okay, so keep this separate from the causality, the discussions around causality. I'm assuming for now that T is randomized. If it is not, you still have to deal with it as you would with any other parametric model, right? So you don't get a free lunch here, right? You have to deal with the problems as they come up. All we're doing is we're saying, look, given kind of the structure of your problem, we're just swapping in deep net parameters for your usual parameters. That's it. That makes sense?
Yeah, thank you.
Yep. Any other questions? No? Okay. Okay, so let's say we can do this, right? So we take these probabilities, we take it to data, we can estimate some stuff. We still want standard errors, like to be able to write our, tables with our parameters, the standard errors and the stars and stuff in order to get published. So how do we do inference? So I'll be upfront. I cannot give you inference on beta evaluated at a certain X, right? Why can't I do that? Well, because, well, that's not true. I could or can and cannot in a subtle way. Let me explain that. So essentially, what we need is we need to be able to kind of get a central limit theorem going, right? And the central limit theorem is going to, obtain if we have enough density of data. So if I say, this is truly at the individual level and this is a beta, well, the construct of n going to infinity goes away, right? So we can give you inference for objects that we can stick an expectation on the outside. That's first. And I'm just giving you intuition here rather than give you formal theory, just so we kind of, we can understand what's going on. So this is the expectation on the outside. H can be any function you care about. All we need is that this function, again, have derivatives. Otherwise, I think you only need 2. But a smooth function of the parameters, so of the x's, and even of some counterfactual treatment. So you can say, what happens to profits if I charge a different price? So a true counterfactual like that, we can handle here. And what we want to do inference on is this average construct mu. So this could be average profits or willingness to pay, average willingness to pay, average anything. Okay? It can also be subgroup averages, which I'm not going to talk about here, but you can say, what's the average treatment effect for men? Was there a question?
No.
No, okay. So these could be constructs so if H is the identity and this is just beta of X, this would just become the average treatment effect. But H could be other nonlinear functions, could be profits, and I'll show you kind of fairly complicated examples where H could also be fixed points and things like that. Okay, now the paper and kind of the main kind of feature of what we're doing here is if you want inference on objects like mu, it can be done completely automatically. So the generic influence function for mu is going to be the plugin, and this should now sound familiar to you after you've gone through Whitney's talk. So there's the plugin piece, and then there is this whole adjustment term. Okay, now there are 3 pieces in the adjustment term, and you should be able to recognize those. The first is kind of the derivative of H with respect to the parameters, right? So that's H sub theta. So if you want some intuition, think of this as the delta method, right? So I want to do inference on mu, which is essentially the average h. So I'm going to take the derivative of h with respect to theta. And then this, if you remember your theory from maximum likelihood, you should recognize this. This is the inverse of the Hessian of L, but it's essentially the inverse of the Hessian, but before that, we're basically taking conditional expectation. So you're taking the Hessian with respect to theta, you're looking at, for a given set of x's, what's the average Hessian, and then inverting that here. And then L sub theta is the residual, right? So it's the gradient, but in a loss function or a likelihood, this term kind of on average should be 0, evaluated at the true parameters. And all of these pieces, the beauty of this is that you don't have to ever do any math, because the automatic differentiation engine will give you all these pieces just by asking for it. Okay, so I know it looks kind of messy a little bit, but it's not. It's really, really simple. This part's just a plugin. So whatever h you come up with, once you have the parameters, you're just going to stick it in there, evaluate this h. This is just the derivative of that h. So that you can do by hand if you want, or you can just ask the computer to do it for you. The more complicated parts are these two, but this is just the gradient of your loss function, which you had to do anyway because you have to maximize or minimize the loss function. And then this is just kind of the Hessians that we typically get, but just averaged for each x. Okay. And if you have that, and you do a little bit of cross-fitting, just like you may have seen before, which I won't go into now, you get your central limit theorem, right? And now you can construct confidence intervals, standard errors, whatever else you want out of it. And just to give you some intuition, let's take this really simple example. But it's not as simple as you think, but you can tell me what. So imagine that your model, your structural economic model, is a linear model, but now you've got alpha of x plus beta of x prime treatment. So this is why I said it's not a simple linear model, in the sense that this one, t could be a vector valued treatment. And I've said nothing whether or not it's continuous or discrete. Okay. Your loss function is mean squared error. Okay. And then in this kind of, if now let's pretend like this is just a binary treatment effect, if you will. If it were a binary treatment effect, your influence function would simplify dramatically. In fact, it would simplify to exactly the influence function adjustment that you would see under double machine learning. Not approximately, it would be exactly the same thing. The beauty of this is over here, if you plugged in, if this was binary, so this is actually bad notation here, this should just be beta t here. And I've saved some space by not making it a function of x's. But so this is your residual term, and then this is your all the other terms that kind of make up the influence function adjustment. What I'm trying to get at is, like, this particular influence function kind of nests some of the other influence functions that we have seen in the past, whether especially for like binary treatment effects, or Brian Graham has some papers on kind of for some other types of structures. But in general, as long as kind of the broader assumptions that we've made hold, you're going to get influence functions that kind of make sense. A couple of caveats. There's no guarantee that the influence function that we are getting here, or the influence function adjustment that we're using here, is using the efficient influence function. There's no claim, there's no guarantee, but it seems like in the context that where we have seen, or where we know the efficient influence function, it happens to show up. So this is for those who are technically minded here. But from a practical point of view, all you need for the construction of your confidence intervals is this simple formula. Okay. Before I go on to applications, like, any thoughts, comments, questions?
It does seem like it's you say it's the average treatment effect, the one if we look back to the treatment function, but you are also conditioning on X, right? So why it's not the conditional average treatment effect?
So the way I've written it out over here, it's easiest to see, right? So imagine that you wanted the average treatment effect. This would be taking expectations over. So how do you actually implement this? This would be averaging over your entire data set, right? So you're going to stick in your beta of X here. You don't need any T star. You don't need any X. H is the identity function. Well, identity in the sense that it removes the alpha, only retains the beta, right? So now let's think about what happens in this formula. So this H is just beta of H, beta of X. Is that clear?
Yeah.
So if this is beta of X and H is the identity function, we'll take the average in a second, but this inside part, that's just beta of X. Now, what's the derivative? Well, that's just going to be 1, right? Because it's the identity function. This part over here, if you just are looking at the average treatment effect, and if it's a binary treatment effect, this is going to boil down to a simple matrix, a 2x2 matrix, which will have 1 treatment, treatment, treatment square. Like that's what it's going to be. But for a binary treatment, the treatment and treatment square are the same thing. So you're going to get 1 treatment, treatment, treatment. If you project that into X's, you're going to get the propensity score. So this part over here is going to have that inverse propensity score type flavor to it. And then this part is going to be your residual. Now, when I average across the X's, I'm going to get the average treatment effect. Now, that's kind of why that's the average treatment effect. Now, if you say, no, I want to know the average treatment effect for men, you can do that, obviously, where you just, put that conditioning in and you can get the conditional average treatment effect. So otherwise, typically we think of this as being the Kate, the conditional average treatment effect. And when you average over all the X's, you end up with the average treatment effect. That answer your question?
Yeah, it was just also about the standard errors and the like in the conditional case, right?
No, yeah. So I can't. So think of it. That's a good point, right? So if I take it to an absolute granular level, then this expectation kind of, intuitively, again, I'm not being formal here, but to give you an intuition. So think of it this way. So if I have a data set and I have lots and lots of X's, obviously I can estimate the average treatment effect and I can give you some idea of my confidence around that. I can give you some kind of uncertainty quantification around it. Great. Now I say, oh, let's split up my data set and say men and women. Okay, that's in my data set, I split it up, but I can still think conceptually of the idea there's an infinite number of men and infinite number of women. So I can still give you some inference. Okay, fine. If I say, let's now say men who live in Zurich. Okay, conceptually, I can still think of like, oh, lots and lots of men might live in Zurich, so maybe I can take expectations. But as I kind of divvy it up, as my set of X's grows, right? Like living in Zurich in a particular neighborhood with a particular income who are interested in jazz, like as I keep adding X's, it becomes difficult to intuitively articulate a reason why this expectation makes any sense, why n kind of goes to infinity. And therefore, I can't give you inference without more assumptions. I can't give you inference on the Kate. And that's my personal intuitive way of thinking about this. As long as you're comfortable saying, oh, this particular subgroup, I'm okay in terms of thinking that the central limit theorem is sensible, you can still use the framework. So subgroup effects, I say, you might get away with. I think the actual Kates at the individual level, if you truly have lots and lots of X's, so this is truly granular, that's a little trickier. So that it can be done, but requires other kinds of localization techniques. And there's other papers that have given you that, like A.T. and Wager, for example. Okay.
Sorry, another question.
Yep.
As you mentioned, as the number of X's gets larger, When I'm thinking of the Hessian, I'm thinking of the number of parameters. So I guess this would be the number of weights in the neural network.
No, no.
Good.
Notice the Hessian is with respect to the theras, not with respect to what's inside the theras. That's the trick, if you will. This is a much lower dimensional object. In a binary treatment effect case, this is a 2x2.
Okay, thank you. That answers.
Yeah, so that's okay. That's a really it's an important point, right? You could do inference the long way. So if you're a CS person, which people have thought about doing, is you could say, hey, you know what? Let's go back here. And in order to kind of give you inference around some object later on here, all the parameters that are in here, like I can ask the question, if I perturb my data set, how do all these parameters get perturbed? And then I can go down here. The trick we are pulling is we are saying, these are functions, right? And this is not our trick. This is like, Whitney's trick. Like he's used it along with his co-authors in many papers. Is that then we can think of functional perturbations, right? So if you've looked at kind of his papers, like when we take the Guiteau derivative, what we're really doing is we're perturbing kind of the functions here. And that allows us to say something without worrying about, or it's kind of taking into account what could have happened here in the weights and the biases and stuff inside the deep net. And that's kind of so all of these calculations that are being done in order to get to this influence function, that's basically saying, let's just perturb theta, and that's going to account for any other kind of sources of perturbations that could have come in from whatever sources we want. So we're ignoring the fact that there's a complex structure behind theta. But you could do it that way. That would just be infeasible. I guess that's where your question was going.
Exactly.
Yeah.
Okay. Thank you.
Yep. It's a good question. Okay, now let's talk about, I have about another, say, half an hour or so before I open it up for questions. I'm going to give you a simple and like increasingly complicated examples, right? And then again, like I said, ask questions. So the simplest one I can think of is this paper that I have with a couple of my colleagues here. And this is the binary treatment effect stuff, right? Like, and by the way, I'm going to ignore the standard errors and stuff for most part because they're now automatic. But when it becomes interesting and different, I'll talk about them. So a classic example, kind of in a marketing context, would be, imagine that you want to send out advertisements or catalogs to a whole bunch of customers, but you want to do that personalize at the individual level. This is I've got one slide on this, but essentially this is kind of the generic application of heterogeneous treatment effects, right? My model is linear, and my Ks are defined as beta of X, and the optimal policy that maximizes profits or return on investment is going to be, hey, make sure that you only target people for whom, the cost of targeting them is low enough, right? So the treatment effect has to exceed the cost of treating them. And if that's true, then that's your optimal policy. Of course, you can use this to evaluate kind of profits with actual data. We do that, and the DNN does a reasonably good job, but the forest actually does a little bit better in our application.
What are M and C?
What was that?
What are M and C? Well, there's a little
M and C. Okay. Let me break this down more. So think about what return on investment is. So C is the cost of targeting. So in order to get a printed catalog out to you, it costs about $1. So just to give you a context of the scale of one campaign that a company might have is if you've got 120 million customers and you send them a catalog, that's going to cost you $120 million for one campaign, right? So for an individual, let's think of this as $1. It's going to cost me $1. This is my treatment effect. So if I treat you, I get this in terms of revenues minus what if I didn't treat you. We know that treatment effect is just this Kate, the conditional average treatment effect. And M is the margin of the revenue that kind of you recover. So that might be whatever, 20%, 10%, 30%. So the margin times the revenue is kind of what your profits are. C is what your costs are. And this you don't care or don't care, doesn't matter. But essentially this term over here gives you your profits, just rewritten slightly. It's saying that your treatment effect has to be greater than your cost over your margin. So kind of your qualified cost equivalent.
Okay, that makes sense. Thanks.
Okay. Again, the economics, you can change this. So you can change this from Y being, Y could be health expenditures for for example, or savings, if you will, and this could be a financial intermediation or education program, or some labor market intervention. Everything kind of, should I kind of target you with the intervention? Well, yes, you should target the person if their treatment effect exceeds the cost of targeting them. That's basically like the simplest example of using heterogeneous treatment effects that you can come up with. Okay, let's take a little bit more complicated just to see like why this framework is useful. So this is a paper, like we're going to replicate a paper in the QJE by actually two of the authors are my colleagues here, Sandel and Marianne. And it's about advertising for loans in South Africa, so for like 4-month loans. And the question they asked in their paper was like, does the content of advertising matter and how much can we quantify that? So what's the outcome? Now you'll see like where I don't have to change my framework that much. I'm going to move from a continuous treatment like here to a binary treatment. A binary outcome. Misspoke there. So the outcome is, did you apply for a loan or not? This time it's a scalar outcome and discrete. But now your policy is more complicated. So you've got 12 different characteristics of the ad. And so these characteristics are things like, was the loan amount mentioned? Was the loan term mentioned? Was something about the competition mentioned? Was there a photograph? Was the photograph of an African, of an African male or female? Like those are all the characteristics that describe the ad that went out. In addition to that, there's also a randomized interest rate. Okay. And you have 11 different characteristics, some of which are continuous, some of which are discrete. Now you may say that's not a lot, but it is what it is, right? And you have an economic model of the relationship between the treatment and Y. Okay. And in their model, they think of it as a probit model, like a binary probit model. You could have chosen something else. But they don't have any rich heterogeneity. They don't use this to characterize heterogeneous treatment effects. That's what we will end up doing, just as an example. Now, the first thing you might want to know is, well, do the marginal effects actually replicate, right? So theirs is a randomized experiment. So in their example, all the policy and all the treatments over here, including the interest rate, have been randomized. So we should be able to replicate their results, and we do, right? So if you look at the confidence intervals, what was published in the paper kind of fall in those confidence intervals. So that's kind of comforting, right? And so, by the way, this DNN marginal effects, that's based on the framework that I just showed you. But notice that nothing changed in terms of our structure of computations, even though we have 13 different treatments now in the same model, right? So we went from a binary treatment to a 13-dimensional treatment, but the math remains the same because, just to remind you, right, the treatment kind of just the same formula applies here. Nothing changes. Just now, this, to the person who asked the question, this becomes a 13 by 13 Hessian now. That's it. Okay. But you get to look, these are the Kates, right? So you get to see that, oh, look, there's considerable heterogeneity. And the point estimates are kind of close. And this is the confidence interval for the average computed using our method. So this is for the interest rate coefficient. There's quite a bit of heterogeneity. But there's heterogeneity in the ad characteristics too. There's tons of heterogeneity in there. And so the question you might ask is, okay, great. Now we have done this. What could we have done with this framework that the original paper didn't do? So what we're going to do is show you that you can do counterfactuals and do inference on counterfactuals. So imagine that the the bank wants to maximize profits. And this is a very stylized profit function, so bear with me. So there's a loan amount, okay? There's the probability of applying. If you apply, I'm going to make some interest, the interest rate is R, off you, but there's a chance that you'll default and you'll run away with the money and I make nothing, right? So that's in here. Oops. Now, if you're a firm and you kind of know a little bit of optimization, what you're going to say is, oh, let's maximize profits and pick out my interest rate. And you get a first order condition. And that first order condition leads you to a solution for the interest rate. It just happens to be a fixed point, right? So if you've ever done anything with like logit or, binary choice models, you'll know you can't kind of solve explicitly for the optimal price. This is similar here. So you get this fixed point, but note, here's what I want you to think about, right? We don't have this in closed form. So the optimal interest rate is not in closed form, but it's easy to see that it's going to be a smooth function of the parameters, right? I can use the implicit function rule to differentiate R with respect to theta. So that's doable, okay? Which means I can do inference on any function I want evaluated at the optimal interest rates. So this is a real application, right? So if you hadn't taken kind of heterogeneity seriously, you wouldn't be able to do any of this. But now we can personalize the interest rate to each X and ask you what profits will accrue, and then also tell you like what are the statistical kind of guarantees I can give you around those profits. So here's an example, right? So for each of these lines is an individual set of X's. And this is solving the fixed points. The red dots are the fixed point solutions for this equation. So this is the straight line is the left-hand side, right? So that's this. Whoops. The downward sloping lines are this right-hand side. Each one has a solution, and I've just pushed it down. So this is the distribution of optimal interest rates that you would offer in this data set, and ranges from maybe 5 and some percent all the way up to 30 some percent. I can then use that and say, okay, on average, what would the interest rate be? That's going to be about whatever this number here is. And I can give you a confidence interval for that number using exactly the same formula. And all of this is done automatically. I don't have to kind of do any extra math, even though there's a fixed point embedded inside the problem. Okay. Not only this is kind of inference around the average interest rate. I can change it and say, hey, evaluate profits at those interest rates and give me what the profits would be and give me confidence intervals around the average profit that I would make from this policy. And I could give you that because profits is just another smooth function evaluated at R star. Ultimately, this is theta of X going into a smooth function, going into a smooth function. So my H is just this complicated thing. Okay, again, let me pause here because this is kind of there's a few important pieces here. We started with a really simple model. So this thing over here, typically, like you would use a binary logit or a probit. That's exactly what we've done, except that just like before, oops, not here. Just like before, I've made the parameters functions of X's. What that allows me to do is to get this heterogeneity as a function of those 11 observables that I have. Using that heterogeneity, I can then come up with an optimal interest rate for each set of characteristics, right? I can find that interest rate by solving those fixed points, and I can tell you what the profits of that personalized policy would be had I charged each individual a personalized interest rate. Of course, I can also impose any other policy I wanted and evaluate profits for that. Okay, let me take a second to see if there's questions here before I move on. No? Okay. Hey, you can do, we have done this with pricing also. I won't bore you with this. I have about 20 minutes, Simon?
Yeah.
Okay. Let me run through the application, see if I can show you some simple code. So here's a pricing example. I think I'll make a slightly different point here that you'll see in a second. So here, this is a paper with JP Dubey. It came out in the JPE last year, where we ran a randomized experiment with a firm called ZipRecruiter. We randomized prices from $19 to $39 in the field. Use that to calibrate a demand model. And kind of optimize prices, just like you saw with the interest rate. Now, as part of the review process, one of the reviewers who was kind of the ML expert suggested the following. Said, hey, why do you have to have this structure? The whole idea of like machine learning is that you can learn from the data what's going on. So ignore X's for a second. I'm going to give you a small problem to work out. Imagine that you have this kind of randomized pricing experiment data. And you said, okay, I'm going to project sales, in this case, conversion or purchase, onto prices flexibly. But I don't know the demand model. I'm not willing to assume that this is logit or something like that. Once I do that, what I can then do is just stick that into my profit function. So this is demand. Here's my margin. Maximize to get prices. And, you have code to do random forests. Fantastic. So I'm going to use random forests to estimate demand here. So here's the data. You estimated this using forests. You estimated the demand function. And my question to you is, what is the optimal price? What do you think the optimal price here is? Take a guess. The current pricing is $99. This is a relatively inelastic demand function. If you did this exercise where you took random forests to estimate this non-parametrically, plugged it in, maximized prices, you could do it for one person, or you could do it for the average or across people in the marketplace. What do you think prices would be? Somebody take a guess.
What's the definition of convergence rate?
What's the definition of convergence rate?
Not convergence rate, conversion rate. The y-axis on that graph.
Just think of that as purchase. This is the proportion of people who purchased. Okay, whatever answer you may have guessed, it's not going to be the one I'm going to show you. And that's going to be the answer every time. Why?
You can just get elasticity of demand beyond. Elasticity of demand beyond one.
Good. That's the typical economic answer, but that's not what's going on. This is machine learning is to blame here, not economics. So it turns out that the way a forest works, or any machine learning approach works in general, is it's really good at saying something that's within the data, right? So you would, and in binary treatment type effects, we don't see the problem, and I'll tell you why we don't see it, because the binary treatment exhausts the entire space of decisions that you could possibly have. Now, when you're optimizing prices, you are evaluating these prices, but you're also evaluating prices in between $299 and $399. You're also evaluating prices that are less than 19, and you're also evaluating prices that are more than 399. That's what optimization does. Great. So far, so good. Now I want you to think about what happens when so you've estimated a forest here, right? For F, you've got this F hat. What is F hat going to say demand is going to be at $400? How does a forest work? Well, a forest works by constructing trees, right? And trees are partitioning functions. So basically, it's going to have like a step function. And once it gets here, it's going to be a flat line. So at 400, your best guess of demand is going to be what it was at 399. That's just how trees work. And because you're averaging trees, you're getting to get a forest, it's the same thing. But at 400, it's going to be, let's say, 10%. At 4,000, it'll be 10%. At 4 million, it'll be 10%. At 4 billion, it'll be 10%. At infinity, it'll be 10%. You guys see the problem? ML doesn't have tools to extrapolate or interpolate without more structure. So it doesn't know what to do outside. So it does whatever the stats tells it to do, which is just project out this way. Now you may say that, well, that's stupid. Why would I let that happen? I'll force it down. But if you force it down, you're using structure. You're not learning the structure of demand. You're imposing the structure of demand, which is what economists do. You guys with me?
A quick question.
Yeah.
Would a neural net, if it's reasonably sparsely specified, wouldn't that give you this kind of structure through the generalization properties?
You have to be lucky. You have to get lucky. So think of it, so this is a simple, I don't need a deep net, right? I could use polynomials, let's say.
No. That's the whole point, right? The neural net with the sigmoid activation function, it would dampen what happens when you move outside of the so-called training set. Whereas with the you will explode. So I think what you're saying is, hey, if I use the structure that I know to be correct, what would happen? If you imposed a deep net, let's say with 3 layers, with whatever activation functions you want, it can approximate any function. So then it'll all depend on what's the local curvature over here, right? So it could be that it comes down here and it says, oh, look, this local curvature is going like this, and it goes like this, like it was steeper, then it flattens out. So it flattens out here. That's possible. Like, that's why I said, think of polynomials as your intuition, but it's also possible that in your data, the local curve, just imagine that 399 was slightly higher here. Then you could go up. That's also possible. You could go down incredibly steeply. That's also possible. But those are not coming from any economic structure. It just happens to be the structure of the machine learning kind of element that you're using there, right? So you could get lucky, and get something here. But my point is to show that an accepted type of machine learning like forests will never come down, right? They'll always be flat. But with deep nets, you're right, you could get something, but those are anything outside this 399 thing is not based on data anymore. And even if it was, take, for example, what happens at 4,000. If you used a deep net, you might, without any restrictions on the outcome space, right? That might end up at negative values. If you're learning this purely from data. If you think this is a probability, well, that comes from structure again. And that's the only point I'm making, that using this framework allows you to bring in structure without any major cost. So you're still maintaining the economics, right? And you're still getting the benefits of all the flexibility of your machine learning model, but within the constraints of the economic model. But you should play around with this, right? It's like, don't take my word for it. Simulate some data, try to estimate a deep net, try to estimate a forest, plug that into an optimizer, see how many times you get crazy answers. If you get crazy answers more than once, then you should kind of be worried. Okay, now so I'll ignore this part, but we put in we did lasso, we did deep nets, just to show that how you do the heterogeneity is kind of not important. The heterogeneity itself is important. You can characterize consumer surplus, obviously, because if you have used a logit model, then we know the formula, closed form formula for consumer surplus, and that's kind of nice. Okay, let me see. Do I want to do another application? Let me run through this, and if you're interested, you can come talk to me at a later point. So just to kind of give you an idea of how far you can really push this. So we have personalized interest rates. I've shown you personalized pricing. Those are the same thing. I'm going to now show you that you can
personalized language, right? And so given the context of kind of what's been happening, you might find this interesting. So how do I know? So I get this, this email that says get a $20 open table gift card. How do I know that this language that they used is optimal? Could I have changed this in any which way? Similarly, how do I know this content is correct? Like, how do I know this image should have been used, or this font, or this text? And how do I optimize that? I will not bore you with the details, but the context of the application is to partner with the SNAP program in California, so the state of California. And just to give you an idea what happens, some of you might know what SNAP is. This is the food stamps program. So if you are poor, you go through kind of a process where they interview you, they look at your documentation, and they decide, okay, you're poor enough that you will get, give or take, about $200 a person, $200 a person for food per month. But even after you qualify, 6 months later, you have to fill out a 2-page form. It's called the SAR-7. And it turns out over half of the people who are qualified and are recognized by the government to be poor, if they don't fill out this form, they lose their benefits. So now you're back, right? So the state recognizes this and wants to keep people on, so they send reminders out. And the reminders look like this. So Get CalFresh is the California name for the SNAP program. To keep getting CalFresh, fill out your semi-annual report as soon as you can, right? And the question I had was, can I personalize the language? And I'm going to rush through this because I want to show you a little bit of code. But the reason why you might think that this is not optimal is, think about how nudges are created, right? Like in this case, it's a nudge, but it could be any message. Typically, the sender thinks, oh, there's a bunch of things, this gray area is a bunch of things I could say, but I'm not going to say all of them. I pick one element, and that becomes my treatment, my nudge. And then I see what happens after that. But, why don't we have multiple nudges? Because there's different people, right? There's heterogeneity. But in order to do that, we'd have to learn the preferences over language. That's kind of hard. So let's build a machine to do it. How do we do that? This was the original nudge that was going out from the state. I'm going to steal an idea from Chomsky called context-free grammars. Doesn't matter what it is, but think of it this way. Essentially, I can take an image, I can break it up into a head, into a torso, into legs, and I can switch them out and they'll create new images. Now think of that with language. If I told you there are 3 features, blue, orange, and green, they're both, all 3 are binary, and I tell you that there is structure or grammar in the language, blue before orange before green. And if I now give you a number, 000, you should be able to see a message. Mary got on an airplane to Chicago. So that's a bijective mapping between language and a vector of numbers. Great. Now I know how to convert language to vectors, vectors to language, which is not true of like GPT and everything else. They're not bijective. You can't go backwards and forwards. Uniquely, at least. So I can't optimize language there, but so I have to do something different. Okay. So I take their original thing, break it up, and add my own. So this is my language, if you will. So the salutation is the starting point. Hi, hello. So I could say hi, or I could say hello. Then I have to say get CalFresh here because I have to identify who the source is. The consequence is to keep getting in order for you to keep, to avoid losing, in order for you not to lose. And those of you who are behaviorally minded will see that this is either a status quo or a loss frame. And similarly, I keep going on. My language can say 14,000 different things. So it's a small language, right? And so my personalization is going to be, which of these 14,000 ways of saying things should I say it to a given individual? The model is trivial. Here's the features. There's 19 features. People have heterogeneous preferences over the grammar of the language. My outcome model is trivial. It's just a binary logit. I replace that with a deep net. Estimated. I don't have data, so I run an experiment, but the experiment only needs 19 messages, even though I have approximately 14,000 messages that I could evaluate. Why can I do that? Because of this linear structure of utility. So I'm making strong assumptions about how these preferences work. That's kind of my structure. That's my economic structure. ran my experiment just like before, and you'll see this is the control message. Some messages are worse than control, some messages are better than control. Tons of heterogeneity. I can estimate the parameters. Here's the control message, but let me bring your attention to the first one. So look at high. High was the baseline. On average, this is the expected beta of X. Hello is better. So I can switch from high to hello on average. If I do it by average, I'll get a new message. I can read it out from the table. Hello, whoever, in order for you to keep your CalFresh benefits next month, you must fill out an update by October 11th. Do this now at. That's an English language message that I can just read off this table. Obviously, there's heterogeneity, just like before that I showed you. So I can personalize. This is the predicted probability of filling out that form across the 14,000 messages for one person. And then I can just pick out which message would work. This is the predicted probability. Different people will have different optimal messages. I'm not going to bore you with kind of validation exercises, except that we did this in the field. The numbers kind of did not work out. We can have a whole discussion of why not. But overall, we got a 17% improvement in filling out the form rate, if you will, or recertification rate. Okay. I know I have 5 minutes. So there's a whole bunch of other things that come up. For example, personalization is good. In this campaign itself, we got $14 million more to poor people in the data, not looking at the model. So I presented this then at the USDA, and if you scaled this to the US, we are talking about big numbers. The incremental effect, just because of using personalization or that heterogeneity piece, that's about 1.75 billion. Okay, so there's a whole bunch of other things. I'll put these slides up. If you're interested, you can always kind of, email me and we can talk about it. But before I get there, I'm going to stop this share and start a different one.
Out of curiosity, were you looking at interaction effects with the,
Yep.
with the language? Like,
Oh,
in other words, if you start by saying hello, like, could that then affect whether something later in the message is better?
Yeah, so the problem with that is the dimensionality blows up dramatically.
Would it be possible if you had like many more observations, or?
Yes. So unfortunately, think of it this way, right? Like currently, the number of observations are dependent on how many people signed up for SNAP and became eligible for renewal. So I don't control that. There were 15,000 in 1 month, and then later on, there were like 10,000. So it's limited by kind of reality, not by choice. But you're right. Like if I was doing this for, let's say, at Verizon, or like, then we have 120 million and we can do a lot more. And we have actually. Turns out that including those interactions give you a little bit of a bump, but not dramatically. So you get improvements like 10% or so. But these things can now, we are working on a different version using kind of language models, which we have already kind of implemented, and those give you much bigger bumps, but we can talk about that another time. Okay, I have a few minutes, so let me just see if I can pull this off. Can you guys see this?
Yeah.
Okay, is the code even legible? Is it big enough, or should I make it bigger?
The only thing is that your window is in front of the code.
Let me shift that.
Sorry.
No, it's better.
How about now? Is that better?
Yeah.
Okay. Okay, so just to give you, and I'll share this code also. It's like seriously simple. So I'm going to use R. It's like, you can do this obviously with Python, but I'm just as a proof of concept, I'm going to use R to do it. There's a package in R called Torch, which is basically a native call to the Torch package. So it is not going through Python. It's just calling the C++ library at the back end. I'm going to generate some data. Let me show you what that data is. Now, this is the part that may or may not work. You can't see my plot, unfortunately. Can you guys see the plot or no? Okay, let's try one more thing just to show it to you, and I'll switch back. How about now?
Yes.
Okay, so this is the, I've chosen a treatment effect function, which is kind of difficult. So I've just taken two of the, on one particular dimension, x1, it looks like this. So there's got some like thin tails over here, and then there's this fat kind of middle, and you've got this curve. Okay, so I'm going to try and kind of learn this function from kind of a 5-dimensional x vector. Okay, let's go back. Share screen again. Find my window. Oh, I'm back there. Stop that share. Let's try this one again. So apologies. This should I? Which is a little. Okay. You should see that again. Okay, so that's what the. So that's basically, here's my function for my true beta. There's x's are in 5 dimensions, but I'm only using dimensions 1 and 2 to generate that pattern. I'm going to also generate some alpha, some propensity score, so that it's kind of correlated with the treatment effect. But here's my generative linear model. So it's going to be y is alpha, beta, treatment, and some random numbers. My architecture is going to be 2020. So I don't know what the function is. So I'm just going to use a very simple architecture. So two hidden layers with 20 nodes each. The entire code to structure the deep net is like, essentially a few lines. If you know this stuff, then it should be trivial. Some learning rate and optimizer setups. Then I'm going to train this whole thing. I'll assume that you know this stuff, but it's not hard to kind of figure out. So we're doing this in real time with a reasonable size data set, which is like you might run into, right? So you might have a 10,000 observation data set with 5 X's with, a treatment effect and an outcome. Like that's not a unreasonable data set to kind of be working with. Usually it goes faster than this, but while it's training, let me just tell you what we're going to do after that. We're going to extract the results, and then I'll show you this plot, but I'll show it to you later because otherwise I'll have to keep switching back and forth. But the inference piece, here's my prediction, here's my loss function. But the trick is everything over here that I'm showing you, I know you won't be able to pick it up like quickly, but this is just computing the Hessian and the gradient automatically, taking the inverse of that Hessian, just like I showed you, calculating the gradients, taking an H function. In this case, I just want the average treatment effect, but in the example over here, I've got a logit. You can even do like surplus functions and stuff. And then everything else is straightforwardly automatic. And just to make sure that I'm getting the right answers, I've compared this. What just happened? I've compared this to the analytical formula from double machine learning because this is a binary treatment effect with continuous outcome. So we know exactly what the efficient influence function is. And you can see that the doubly robust estimator and my algorithmic or auto D, whatever torch approach to doing it is pretty much spot on. You guys see that?
Yeah.
Okay. Let me just show you one last thing and then I'll stop. So let's look at the recovery of the function. Stop the share. Okay, it's not perfect, but it's not terrible either. Okay, I am out of time, I think. So I'm going to stop here. Sorry for going over a few minutes. Hope, I know I packed a bunch in there, but the slides will be available, and I'm happy, like, if you have questions, feel free to kind of just email me, and I'm happy to kind of talk about things.